What I'm going to do now is take my experimental frequency response data and produce a transfer function. So I can go quickly and easily from one to the other. Okay, something's gone slightly wrong with the overlay on the dotted lines, so bear with me on that one. And I think you'll find, yeah, there's a whole list of instructions down there. I'll go through it reasonably quickly with you, just so that you can see the process, okay? And every time I do this, I'm going to be cross-referencing against my little shopping list of different graphs. So, always start off with the left-hand side, the low frequency end, and ask yourself a simple question. Is there a gradient or not? Yes, there is in this case. It starts off with a gradient of what looks like minus 20 decibels per decade. Beware, these are logarithmic plots. The intercept on this axis is meaningless because that's not 0, is it? It's 10 to the minus 1. So with a logarithmic plot, don't get hooked into looking too much at where it intercepts the axis, because I could keep extending that axis leftwards as far as I like. So anyway, I've got minus 20 decibels per decade of slope. Which of my building blocks actually will give me that? Well, can't remember. Let's have a look. Oops, that way. There's my shopping list. Which one of those things gives me a slope of minus 20 decibels per decade right from the beginning, right at the left-hand side? Integrator, thank you very much. It's the only one that actually starts off with that gradient. So that first bit, I would say right now, there's an integrator present. So I'm trying to work out my transfer function, and I reckon there's an integrator present. If it was an integrator by itself, where would it intercept 0 decibels? Just an integrator with nothing else associated with it would cross that axis at what frequency? 1 radian per second. Well remembered. Does this one cross through the 0 decibels line at 1 radian per second?
No.
No, it doesn't. Something has pushed it down or pulled it up, because 1 radian per second is over here. So my integrator has actually been pushed down. What will do that is a gain. How big is the gain? Well, I'm lucky in this case because I've actually got 1 radian per second on the scale, so I can see. And that 1 radian per second has been pushed down by that much, hasn't it? Which is about 10 decibels. Or strictly speaking, minus 10 decibels. So all I need to do is convert minus 10 decibels back into a ratio, and I know what K is. 20 times log to the base 10 of the ratio equals minus 10. It's too late in the day to do this in my head, isn't it? But get a calculator. Minus 10 equals 20 times log to the base 10 of the ratio of K. Minus 0.5, isn't it? Minus 0.5 is the log to the base 10 of K. So K is... well, it's less than 1, I know that much. You can work it out. If you've got a calculator, just go through that. You can quite quickly work out K. Once I've figured out what's going on at that left-hand side, all I now need to do is to go up the frequency axis, looking for corners, looking for changes in slope. Okay, because I've dealt with gains and integrators and differentiators, which are just straight lines. They don't have corners in them. And once I've sorted those out, right at the left-hand side, if I can identify the corners, I can pick out the other bits and pieces. So where's the first corner? Fairly obviously there it is, where those two intercept, if you pretend that the dotted lines are at the right slope. What is the change in slope? Okay. I don't care what the actual value is, but what's the change as I go around that corner? I start off at minus 20 decibels. I end up at plus 20 decibels. So what's the change in slope? Plus 40. Okay. Go back to your little shopping list. What is it that gives me a plus 40 decibel change in slope? Anything in there give us a change of plus 40 decibels? The second order lead. Yeah, this one. This one down here goes from 0 to plus 40. So, I reckon, I have to redo all my scribbles on this. Anybody worked out K yet? There's my second order lead. What's omega n? Well, omega n is where the two lines intercept, which is 2 radians per second. Okay. I'll talk about zeta later. I can estimate zeta as well, but I'm going to pass that over. Where's the next corner? Or rather, what's the change in slope at the next corner? Next one's over here, isn't it? What's the change in slope? Minus 20 decibels per decade. Back to the shopping list. What gives me a corner of minus 20? No corners on an integrator, it's a straight line. So first order lag. It's turning down, it's got a negative corner, so that means that the S terms are in the bottom of the fraction, it's a lag, and there's only a change of 20, so it's a first order lag, times 1 over 1 plus tau S. Corner frequency here is was just over 10 radians per second, so that, and tau is 1 over that, so it's roughly 1 over 1 plus 0.1 S. Where's the next corner? Well, it's over here. What's the change in slope?
First order lag.
It's first order lag. Jumping to the next question. Change in slope is minus 20 decibels per decade. That's another first order lag. What's the corner frequency? That's 10 squared, that's 100, 200, 300. Tau must be 1 over 300. Where's the next corner? There isn't one, is there? I've run out of corners. Oh my gosh. So I finish. I end. So from that piece of experimental frequency response information, all I need to do now is to multiply this lot together in my best handwriting, and I've got the complete transfer function for that system. Okay, so I can go from a transfer function to the drawing, or from the drawing to a transfer function, and it's really not all that difficult, so long as you're okay messing about adding up pictures. You'll notice I haven't done anything with the phase information. What I tend to do is to use the phase information just to confirm that what I've figured out from the amplitude is correct. Okay, so we said right at the left hand side, down over here, we only had an integrator and a gain. Okay, so you look at the little pictures on the phase plots and you find that the integrator contributes a constant minus 90 degrees. Okay, the gain doesn't have a phase shift, so my plot should start off at minus 90. So that's in agreement, is confirming what I've thought. My second order lead should contribute, it starts off at 0 and it goes up to plus 180. So if I add that on top of what I already got, it should go from minus 90 towards plus 90. It doesn't quite get there because something else is happening, but it's looking reasonably convincing. Okay, that phase is going more positive, so it's obviously a lead kind of thing going on. It's also doing it fairly quickly, which suggests that it's got a low zeta. I've got a lagging corner here, first order, so that's going to bring it down again by 90 degrees, so this is turning down. I've got another lag corner there, and that's bringing it down further again. So I've got minus 90, plus 180, minus another 90, minus 90. If you add them all up, you should end up back at minus 90. So you can look at the phase information just to confirm that the analysis you did from the amplitude plot is correct. And you can pick up a few extra bits of information about things like zeta, because that phase change corresponding to the second order bit there is quite fast. So that suggests a small zeta. Okay, and it talks all the way through the thing that we've just done in there. So that document linked to this lecture basically goes through, and this is how you do it. Okay, Bode plot to transfer function to Bode plot, and that document explains exactly how to do it. Okay, and the easiest way to get to grips with those is a bit like the root locus plots, is just to practice them. Just to sketch these things and it will make sense. We've just done this. This is system identification is what I've just done, which is finding a transfer function from the experimental data. Okay, same rules, same shopping list. I forgot I had this example on the slide. There's some experimental data. I'm going to do this one. This is much sparser data. There's less to see here. Okay. The green dots are phase, the red dots are amplitude. And what I do is start at the left-hand side and see what's going on. Okay, so in this case, I'm going to start off at the leftmost point. I'm going to try putting some straight lines and see how well they fit the data. That's rubbish. Kind of okay. That's rubbish again. So I think that that's first, at least the first couple of data points is best served by that line at minus 20 decibels per decade. And then things move away from that. So I think there's something going on. So let's have a look at the next few bits of data. And then what I'm going to do, because there's so few pieces of data, is I'm going to start at the other end. And again, to see which gradient fits best. Minus 20 is not very good. Minus 40 is not very good. Minus 60 is looking more like it. I went up to minus 80, that would be rubbish as well. And those things intercept at a frequency of 20 radians per second. Okay, so based on what we've just done, my data is starting off with a slope of minus 20. So what have I got?
Integrator.
An integrator. It's the only thing that's got an initial slope of minus 20. There's an integrator present here. Then I've got a corner. where the slope changes from minus 20 to minus 60. So what's the change in slope? Minus 40. What gives me a change in slope of minus 40? Close. It's going down.
Is that not a lag?
So it's in the bottom. It's a lag. Okay. So we've got an integrator and a second order lag. I forgot to ask you about the gain. Is this an integrator by itself, or is there a gain involved? It should pass through this point here. 1 radian per second at 0 dB. It actually passes through a point probably much further up. So it's actually got a positive gain. Yeah, that line's been lifted up. I could extrapolate that and see where it's hitting the axis, probably somewhere around 12 decibels. Convert that back into a ratio, I've got my gain. Conversely, if you don't have the luxury of having the 1 radian per second point, you can work it out. Because if all we had was that line, then the whole transfer function is k times an integrator. Okay. 1 upon s, this is sinusoid, is 1 upon j omega. So g equals k over j omega. That's got 3 variables in it. If there's any point on that line where I know 2 of them, I can work out the third. So in this case, I happen to know that the gain equals 1, or the amplitude equals 1 at a frequency of, what's that, 2, 3, 4, 5, 5 radians per second. So G is equal to 1 when omega is 5, so K must be equal to 5. G equals K upon omega. So you can work it out as well. Okay, so there's my corner frequency, 20 radians per second for my second order lag. The other way to figure out zeta is to look at the difference between the real data and the idealized straight lines. Okay, and in this case that's got 6 decibels of difference. That's critically damped. Okay. If it's less than 6, it's underdamped. If it's more than 6, it's overdamped. There's the phase shift, which should confirm what we've got. Follow the example on the handout. I did them in the wrong order. Okay, so we've just thrashed through frequency response analysis. We've actually done a test. We had our position control system at the front. We could take measurements from that. We've looked at how to plot those measurements, primarily focusing on the Bode plot. And if we've got a Bode plot, we've seen how to extract a transfer function from it. Okay. And if we had a transfer function, we've seen how to produce a Bode plot. So altogether is a really powerful package that you can use to figure out what the systems are doing. Okay. And I'll give you a bonus that makes it even more useful. If you wanted to see what a system was, let's go back to the nuclear power station example. Okay. You can generate frequency response data like this by making very small perturbations onto a steady signal. So if you've got dialed into your power station, I want 50 gigawatts please, and it's there sitting stationary at 50 gigawatts, and you think, I've forgotten what the transfer function of this thing is. I could inject a very low amplitude sinusoid into that system, so it could vary between 49 and 51, which isn't going to cause too much damage, and I can get this same frequency response data just by looking at that perturbation. I don't have to make large changes in what's going on, so I can extract this information on a working plant. I can extract this data, frequency response tests, on a working plant, working equipment, without troubling it too much. I have to give it a little bit of a shake, I have to put a little bit of a sinusoid in to see what's happening, but I don't have to make massive changes to its operation. Okay. So all in all, it's a really powerful tool to use frequency response information. Okay, that's a fairly concentrated hit of frequency response. Have a look at that PDF and make sure that you understand how to swap from transfer function to plot and back again. Okay, thank you very much.